Hello everyone, and welcome back to the Fluctus Channel. The U.S. Army's search for unmanned ground vehicles begins with one hard lesson for modern combat. The most dangerous ground missions are often the ones that come before the main force moves. Reconnaissance, route clearance, security patrols, resupply, and first contact can expose soldiers to mines, ambushes, drones, artillery, and anti-armor weapons. Robotic vehicles promise a different approach, placing sensors, cameras, weapons, cargo space, and mobility in front of the soldier instead of placing the soldier first. That need is tied directly to Army modernization. Future battlefields are expected to be faster, more transparent, and more lethal. Units may have to move while enemy drones watch from above, electronic warfare disrupts communications, and long-range fires threaten anything that remains still too long. In that environment, unmanned systems can scout danger, carry equipment, extend a unit's reach, and reduce the number of soldiers exposed during the earliest moments of a fight. At Grafenwohr training area in Bavaria, Germany, that future moved from concept to field testing during X-Tech Edge ground strike. From March 2 to 13, 2026, U.S. Army soldiers tested robotic and unmanned ground vehicle systems in a technology evaluation led by the 2nd Cavalry Regiment. Global developers brought emerging systems into a real training environment, while soldiers judged how the vehicles performed against practical battlefield tasks. The trials were not built around polished display routines. Soldiers observed movement, control, responsiveness, terrain handling, payload use, and tactical value. Robotic platforms moved through training lanes while crews evaluated how quickly they could understand the system, send commands, watch sensor feeds, and imagine it inside a real platoon or troop formation. Developers gained feedback from the people who would actually depend on these machines under pressure. This matters because military robotics cannot succeed through engineering alone. A vehicle may look advanced, but soldiers still need to transport it, power it, repair it, hide it, communicate with it, and trust it enough to use it near a dangerous objective. That is why X-Tech Edge Ground Strike joined a prize competition with operational testing. The Army was looking not only for clever machines, but for useful machines. The wider effort connects to the Next Generation Combat Vehicle Program. In August 2019, engineers and project managers from the U.S. Army Ground Vehicle Systems Center and the Next Generation Combat Vehicle Cross-Functional Team demonstrated mission-enabling technologies demonstrator platforms and robotic combat vehicle surrogates at Camp Grayling, Michigan. These early concepts helped explore manned-unmanned teaming, where soldiers in crewed vehicles could control robotic partners ahead of them. By 2020, the Army was already conducting soldier experiments to determine whether robotic combat vehicles could increase the lethality of ground combat units. A platoon-sized element from the 4th Infantry Division tested mission-enabling technologies demonstrators, beginning a series of experiments that would shape future development. In 2022, soldiers from 1-7 Cavalry at Fort Hood took part in Robotic Combat Vehicles Soldier Operational Experiment 2, giving the Army more field experience with control, maneuver, and tactical integration. The direction is clear. The Army wants robotic vehicles that can work with soldiers, not replace them completely. They can push sensors forward, carry weapons, transport supplies, and test routes before humans enter. In Germany, the soldiers of 2nd Cavalry Regiment helped answer the most important question. Not whether robots can move, but whether they can help ground forces survive and win. These events also give commanders a realistic look at sustainment burdens. Robotic vehicles still need charging plans, spare parts, recovery procedures, software support, transport space, and protected communications. A platoon cannot treat them as magic tools. It has to plan where the control station sits, how far the machine can move, what happens when a signal drops, and which soldier has authority to take over. That is why field trials in Germany are so valuable. They expose problems early, before a system is sent into combat. When soldiers criticize a design, struggle with controls, or ask for a different payload, that feedback becomes part of modernization during combat trials. It also shows whether a robot can keep pace with formations already trained for speed, concealment, and sudden contact. The robotic revolution is not limited to wheeled and tracked vehicles. Over the past 2 decades, 4-legged machines have moved from strange research projects into practical military experiments. One of the most famous early examples was Boston Dynamics' Big Dog, developed in the 2000s as a rough-terrain robotic pack animal. Its awkward, powerful legs could recover balance, climb across broken ground, and carry loads in ways ordinary wheels could not. Big Dog did not become a standard military mule, but it changed expectations. It proved that legged robots could cross terrain that might stop small vehicles. Later machines became smaller, lighter, more agile, and easier to control. They learned to balance on slippery surfaces, walk through mud, step over obstacles, patrol uneven ground, and even operate around water, as engineers explored more amphibious and all-weather designs. For militaries, the appeal is obvious. A robot dog can go into a dark building, an empty road, a perimeter fence line, or a contaminated area before a human team enters. Cameras, thermal sensors, microphones, communications links, and artificial intelligence can turn the machine into a mobile sentry. It does not get tired during a patrol, does not lose focus at a gate, and can be sent towards suspicious activity without risking a defender immediately. The U.S. Air Force has tested that idea repeatedly. At Tyndall Air Force Base in Florida, the 325th Security Forces Squadron prepared to incorporate QUGV robotic dogs into base defense and installation safety. The machines were intended to strengthen perimeter security by scouting threats and giving defenders another set of sensors across a large installation. Similar demonstrations later took place at other bases, including training with security forces at Holloman and Klamath Falls. where airmen learned how robotic dogs could fit into patrol and response routines. Training is where the promise meets reality. Operators must learn how to move the robot through gates, around vehicles, over steps, through rough patches, and into areas where wireless control can become difficult. They must understand battery limits, camera angles, blind spots, noise, weather effects, and what to do if the machine stops during a mission. But its value still depends on the person controlling it. The Army has also tested robot dogs for combat-related roles. Soldiers with the 10th Mountain Division and the U.S. Army Combat Capabilities Development Command Armament Center worked with innovative unmanned capabilities, including quadruped systems that could support future formations. Other demonstrations have explored remotely actuated weapon systems mounted on robotic dogs, raising the possibility of sending a weaponized ground drone into danger while a human remains behind cover. That development brings both opportunity and caution. A robot dog can be a scout, guard, sensor carrier, communications node, or weapons platform. But commanders must decide how to control it, when to arm it, how to prevent misuse, and how to keep humans responsible for lethal decisions. The machines are evolving quickly, but the battlefield still demands discipline, rules, and human judgment under pressure. The same move toward robotic systems has reached far above the ground. The X-37B orbital test vehicle is a reusable, unmanned spaceplane built to test technologies in orbit and return experiments to Earth. It launches vertically on a rocket, operates in space for months or even years, then lands horizontally on a runway like a small shuttle. The program began under the U.S. Air Force and now operates for the U.S. Space Force. Its mission is experimental by design, demonstrate reusable spacecraft technologies, and carry experiments that can be examined after landing. The vehicle is about 29 feet long, with a wingspan of nearly 15 feet, large enough to spend long periods in orbit with a payload bay and deployable solar array. Before launch, the X-37B must be transported, processed, checked, and integrated with its rocket. For OTV-5, the vehicle was moved in a protected transport operation before final launch preparation. Technicians handled the spacecraft like a highly sensitive aircraft and satellite combined. Every surface, panel, connection, and support fixture had to be protected before it could be joined to the launch system. On May 20, 2015, an X-37B launched aboard a United Launch Alliance Atlas V rocket on the OTV-4 mission. In later missions, the program continued to increase endurance. OTV-5 landed in 2019 after 780 days in orbit, while OTV-6 remained in space for 908 days before landing in November 2022. OTV-7 concluded on March 7, 2025, when the Space Force recovered the vehicle at Vandenberg Space Force Base after another successful mission. By then, the X-37B had completed 7 successful flights, and Mission 8 launched in August 2025 with test objectives including laser communications and a quantum inertial sensor. The landing is one of the most important parts of the program. After deorbit, the spaceplane descends through the atmosphere, lines up with a runway, lowers its landing gear, and touches down without a pilot on board. Crews secure the vehicle, inspect it, make the area safe, and tow it toward a hangar for post-flight processing. The experiment does not end when the wheels stop. Engineers still recover payloads and study how systems performed in space. One public example is the Naval Research Laboratory's photovoltaic radio frequency antenna module, known as PRAM. It tested the conversion of solar energy into radio frequency microwave energy. The X-37B gives researchers a reusable platform where technology can survive, launch, operate in orbit, return through re-entry, and be examined on Earth. From unmanned ground vehicles in Germany to robot dogs at air bases, and a robotic spacecraft returning from orbit, the same pattern appears. The US military is testing machines that can move ahead of humans, endure harsh environments, carry sensors, support decisions, and reduce risk. These systems are now being driven, walked, launched, recovered, and improved by trained people. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.